Okay, so I'll be talking about hierarchical clustering. This is a very classical and popular form of data analysis. And so why is it popular? Basically because it captures the structure of data at all scales simultaneously. It's a multi-scale structure. And we have some nice algorithms for doing this, okay? Complete linkage, average linkage, and so on. Okay? The problem, though, is that it's not completely clear what these algorithms are doing. Okay? Average linkage, these various linkage methods, they do a bunch of steps that individually seem innocuous. They keep merging things that are close together, and at the end they spit out a tree. But there's really no underlying objective function that this tree corresponds to, which means, for example, that it's really hard to pinpoint the kinds of trees that they're producing, or to say that here's another algorithm that's faster, that's doing kind of the same thing. Or, for example, to introduce constraints and say, we want the best tree subject to these constraints. So in other areas of machine learning, just having a loss function has been really important. And so it would be nice to have something like this for trees as well. And so that was sort of the motivation for the work that I'll describe today. And so what I'll do is I'll propose a cost function for hierarchies, and then I'll give an algorithm that that approximately minimizes this cost function, and then I'll show how it can be used for various things like interactive hierarchical clustering. Okay. So how would we come up with a cost function? So the input to hierarchical clustering is a bunch of points, say in Euclidean space, or more generally in a metric space, or most generally of all, just a bunch of similarities between points. Okay, so the input could be an n by n similarity matrix. Okay, now to sort of keep things pictorial, I'll just assume that this similarity matrix is given in the form of a graph. Okay, so over here there are 6 data points, and these are the ones that are similar. And again, just for simplicity, over here all the similarities are 0 or 1, but in general they will be some sort of positive numbers. Okay, they'll be positive real numbers. And so this is the input similarity. And now we want to come up with a cost function on trees. So for every possible tree, we want to assign a score. Okay, and how would we do that? What's a reasonable cost function? So here's an idea, okay? So the edges over here represent similarities, so we don't want to break those edges. So why don't we, if a tree cuts an edge, then we charge for that, okay? So that's a reasonable thing. We don't want the clusterings to cut edges. But in a hierarchical clustering, you eventually cut all the edges, okay? Because at the end, you just end up with the individual points. So what we'll do instead is that we'll say that we charge for cutting an edge, and the charge is higher the higher up that edge is cut. Okay, so we don't want to cut any of these edges, but if we cut an edge really high up in the tree, then we have a high charge for it. And if it's lower down in the tree, then there's a lower charge. Okay, so let's step through an example of what this cost function would look like. So here's the input graph, and now we want to assign a cost to any given tree. Okay, so here's a sample tree. And we need to say, what is the numeric cost of this tree? Okay, so let's look at the cuts that this tree induces. At the very top, it's separating 5 and 6 from 1, 2, 3, 4. So it's cutting this edge at the top. Okay, this is the edge that's cut. And since it cuts one edge, we'll give it a charge of 1. That top split costs 1. The second split on this side separates 1 and 3 from 2 and 4. So it cuts these. Okay, so it cuts these 3 edges. So we'd normally give it a charge of 3, but at this point it's a little lower down. At this point, only 2/3 of the data remains. There were 6 points, and at this point only 4 of them are left. So we get a discount. So we charge 3 times 2/3. Okay. On this side, we separate 5 from 6, so we cut this one edge. So we charge 1 for it, but only 1/3 of the data points were remaining at this point. So we multiply that by 1/3. Okay, and so on. So if there are any questions, just feel free to ask.
Sanjoy?
Yeah.
So there's nothing in this criteria explicitly which says anything about depth.
That's right.
So are you going to get very deep trees out of this sometimes?
So it's quite possible, but we'll see. So we'll see a bunch of things related to depth. For example, it'll turn out that the algorithm that I talk about later will produce things that are log n depth. Okay, so here's the cost function specifically. Okay, so you get charged for each edge. It's the weight of the edge times the fraction of data that was left when you cut that edge. So let's say there's an edge between I and j. Okay, so then there's an edge between 2 points I and j. When did that edge get cut? At the lowest common ancestor of I and j. That's when that edge got broken. And you get charged according to the number of leaves in that subtree. Okay, the fraction of data that was left when that edge was cut. So I'm not dividing by the n over here, just for simplicity. Okay. So that's the cost function on trees. And so let's look at some properties just as sanity checks, okay? Because we just are trying to cook up a cost function from first principles, and this could easily lead to something that doesn't have that doesn't behave well on even very simple cases. Okay, so let's do some sanity checks. So the first thing to observe is that there's always a binary tree that is optimal. Okay, so even if there could be several optimal trees, but if there's one that looks like this, you can always just separate off one of these subtrees at a time, and you will not increase the cost. Okay, so under this cost function, you can restrict attention to binary trees. The second basic similarity check is that if the initial graph is disconnected, then you do have to start by separating out those disconnected components. Okay, so at least that's true. Okay. So now let's look at some more concrete examples. Okay, let's say you have the graph. Let's say your input similarity is just a line graph on n nodes. What is the optimal tree in this case? Okay. So here are two candidate trees, and let's look at what their cost would be. This is the caterpillar tree that first separates off 1, then separates off 2, then separates off 3, and this is the more balanced tree. Okay? So for the caterpillar tree, this is the first edge that you cut, and when you cut it, there are n nodes left, so you get a cost of n for it. This is the second edge you cut, and when you cut that, there were n minus 1 nodes left. This is the third edge, and when you cut it, there are n minus 2 nodes left. So the total cost is n plus n minus 1 plus n minus 2, which is n squared. So the cost of this is n squared. For this one, the first edge you cut is the one in the middle, and then there are n nodes left. The next one you cut are the 25 percentile and 75 percentile edges. And when you cut those, there were n over 2 left, and so on. And so now the cost is going to be n log n. Okay, so in this case, this would be n squared. And so there's a strong preference for the balanced one in this case by a factor of n. Okay? What I'll show you in a second is if the input is the, yeah, go ahead.
But if you did this iteratively, like in a greedy fashion, it would favor the first one, though, because the cost at every juncture is, 1 and n nodes left, and the other one, you're multiplying n over 2 by n over 2 in the first step, no?
Right. So what you're saying is that if we tried a greedy algorithm where we iteratively did minimum cut, then it would not. But it turns out that greedy algorithm will also not give a good approximation to this objective, and so we'll have to use a different type of greedy algorithm. Okay. Right. So a key property is that if the input is the complete graph, then all trees have exactly the same cost. Okay. So if the input is the complete graph, so there is nothing is more similar than anything else, then every tree has exactly the same cost. And it turns out that a lot of other things having to do with this cost function really rely heavily on this property. Okay, and I'll explain why that's true in a second. So one of the things that implies, for example, is that if you try running this on a planted partition model, then in expectation it does exactly the right thing, and with high probability it comes close to doing the right thing. Something like that. Okay, so let me just explain this property a little more. Why is it that under this cost function, if you start with a complete graph, every tree that you can think of has exactly the same cost, every binary tree? Okay? And so I'll just step through the argument very closely. Okay, so we have this graph, which is a clique, okay? And each time, for every edge, we're going to charge the number of nodes that were left when that edge was broken, okay? So that means that for each edge, we charge at most n, and there are n choose 2 edges. Okay, so an upper bound on the cost is n cubed. It's actually n times n choose 2. Let's just make it n cubed. Okay, so that's an upper bound on the cost. Now we get a specific tree, and we haven't looked at the tree yet, but we know its cost is at most n cubed. Okay, we are going to bound the cost of the tree by just revealing it one node at a time. So we have this tree. We haven't looked at it yet. We know its cost is at most n cubed. And now we're going to open up the top node of the tree, the top split, and then we'll open up the second split and so on. We'll gradually reveal the tree. Okay, so we have an unknown tree, and we're going to reveal one split at a time. And after we've revealed j splits, we'll look at the cost of the remaining part. Okay, and whatever's left, whatever we haven't looked at, we're going to bound by this n cubed type thing. Okay. Okay. So initially, we haven't opened up anything in the tree, and so an upper bound on the cost is n cubed. Let's say that we open up j splits, and the jth split, the jth node from the top of the tree, has a set of size m that it splits into two sets of size k and m minus k. Okay? So now, before we unveiled that split, we were charging m cubed. We didn't know what was going on. We said an upper bound on the cost is m cubed. Once we've opened up that split, an upper bound on the unknown cost is k cubed plus m minus k cubed. Okay, so this is how much the upper bound has changed. M cubed minus k cubed plus m minus k cubed, which is this amount. And that specific cost that we've opened up, the specific split that we revealed, what is its cost? Well, there were m nodes left at the time, and this is the number of edges across the split. So it's exactly the change in the upper bound divided by 3. And in this way, we go all the way down the tree. Initially, the unknown cost was n cubed. By the time we're left at the bottom, we have these n individual nodes, each with a cost of 1 cubed, which is 1, and there's n of them. So this is the cost at the bottom of the tree. And so the overall cost of the tree, the cost of all the splits, is just the sum of these quantities, and it's a telescoping sum. And so it's the initial upper bound minus the final upper bound divided by 3, and it's n cubed minus n over 3. Okay, so no matter what tree you use, you end up with exactly the same cost. Okay, which is, and this turns out to be a helpful property for showing many other things about this cost function. Okay, so we've shown that it has some reasonable properties, and it does something okay with the planted partition model. But all of this would be meaningless if we didn't have an algorithm for it. Okay, and so the first thing is that it's an NP-hard problem. Okay, and this is sad, but it was certainly to be expected because all the other clustering cost functions we know, k center, k means, they're all NP-hard. Okay, so it would be weird if this one weren't. So we have to look at heuristics. Okay, so here's a very natural heuristic. You have this input similarity graph. Why don't you just do a spectral bipartitioning of that graph? Okay, so you get two pieces and make that the top split, and then you recurse on the two sides. Okay, why don't we give that a try? Okay, so the input is this weighted graph, and you recursively do sparsus cut. Okay, so here's the algorithm. You do sparsus cut, and then you recurse on the two sides. Now, sparsus cut is, again, something that is NP-hard. But we have lots of approximation algorithms for this. We have the spectral relaxation. We have the LP relaxation, the semi-definite relaxation. So there are plenty of algorithms for this. Let's say we just use whatever our favorite is, which is some alpha approximation to the sparsus cut. It turns out that if you do this, then overall you get an alpha log n approximation to this cost function. And I'll explain why. Okay, so it's a very simple algorithm. You just do, and this is something that actually has been suggested in many other contexts, recursive spectral partitioning, or maybe not the spectral cut, but any sort of approximation to sparsus cut. And if you do this, then you get an approximate solution to this hierarchical clustering problem. Okay, and so let me explain briefly why that is the case. Where's this alpha log n coming from?
Sanjoy?
Is this true even if alpha is 0? So if you have an exact sparsest cut, do I get an exact solution to this cost function?
Yeah, so then alpha would be 1 in that
Sorry,
case.
alpha's 1.
Yeah.
Okay, great.
Yeah, so right, so that's right. You would still get an approximation, but one thing that I will, so there have been some improved results that I'll also talk about in a sec, right? Yeah.
Why does this create balance? The algorithm tends to create log n depth trees, right? I don't understand why this rule does it.
Right, so we'll see that in a second, okay? And yeah, so the weird thing over here is that the algorithm that we are using is this is sparsest cut, where you're looking at the ratio of the number of edges cut divided by the number of nodes on each side. You're looking at a ratio, and there's nothing in the cost function that suggests a ratio at all. It's just because it's hierarchical that you need to do these ratio cuts in order to get an approximation factor.
Another quick question.
Yeah.
Going back to the algorithm, typically when people do these sparsest cuts, they will enumerate the threshold until they take the size of the cut that minimizes the criterion, like sparsest cut. You would do the same enumeration here for your objective function, or you would use their own heuristic?
Sure. I mean, so you're saying that let's say we just look at one eigenvector. That gives us sort of n candidate cuts, right? And we just pick whichever one had the best objective. Yeah, so that's exactly what you would do in this case too. Yeah.
Like you would use the sparsest cut objective, or you would use CT?
You'd use the sparsest cut objective, yeah, because CT is for the overall tree, so it doesn't really say anything about the. Okay, so you would, yeah.
So I mean, would this be extendable to a very simple additional case where the nodes themselves have costs associated with them, and so instead of counting, you would sum up the weights of the nodes and correspondingly normalize based on the weight of the nodes rather than the cardinality of the nodes?
Sure, absolutely, and
It would be
it would be exactly the same thing. And so I'll actually present a generalized form of the cost function very soon. Okay. So so here's the argument, right? So so we have this cost function that applies to entire trees, and now we're sort of greedily constructing it by doing one split at a time, in this recursive way. So what you can show, and why are we doing sparsest cut? Well, what you can show is that pick any tree you like. If the tree has low cost, then there exists a cut of the graph that is balanced, 1/3, 2/3 balanced, and such that the sparsity of that cut, the number of edges across divided by the number of nodes on the left and the number of nodes on the right, is also very small. So if the tree has small cost, there exists a cut that is balanced and has small sparsity proportional to the cost of that tree. Okay? And this is sort of the key thing you need, of course, in any greedy scheme. And so why is that the case? So you have this tree, let's say the optimal tree, and the tree starts by splitting the graph in two. Okay, but the tree split might not be a balanced split. That optimal tree, who knows? Maybe it's got just 10% of the nodes on one side and 90% on the other. Okay, so the optimal tree might have just 10% on this side and 90% on this side. In which case we keep going. Let's see what the tree does next. Oh, well, we only cut off 5% this time, 85% on this side, and we keep going until we accumulate at least 1/3 of the points on one side. Okay, and so you end up with at least 1/3 of the points over here and at least 1/3 of the points over here. And that's the cut we're going to look at initially, this versus the union of these. Okay, so that's what we're going to, that's the cut AB. Okay, so we pick the smallest case such that we get at least n/3 points over here. And the cut we're going to look at, whose sparsity we're going to bound, is that. A on one side and all of these on the other. And so they each have size at least n/3, so it's a balanced cut. And now, this is the tree, the optimal tree. The edges across the cut are contained in these edges. And so the cost of the tree, in this optimal tree, every one of these edges was cut at a point where at least 2/3 of the nodes were still present. Okay, so for every one of these edges, the cost was at least 2n over 3. So the overall cost of the tree is at least 2n over 3 times the edges across that cut. And so that's all and so that's what we get over there. And so we're in a situation where you get a cut that's balanced. It shrinks the size of the data by a constant factor, and we can bound the cost relative to the optimal tree. And so you're golden. Basically, you can just keep applying this, okay? And so this gives the alpha log n factor. And there's also, you can look at a generalized cost function where you have some other function of the number of descendants. So instead of looking at, suppose you say, well, instead of looking at the fraction of the points that were left when the edge was cut, what if we want to look at the log of the fraction or the fraction squared or something like that, okay? And you can do something similar for all of those. Okay, so now in terms of theory results, there have been some beautiful, more recent work. So Moses, Charikar, and Vagos Chatsiafratis showed that the algorithm that I thought was a alpha log n approximation is actually just an alpha approximation. There was a certain looseness in the analysis, okay? So it's actually, it's actually a lot better than expected. And then there's a very interesting result by Varun Kanade, Vincent Cohen-Haddad, and Claire Mathieu, which said that, look, in many contexts, like in phylogenetics, a cost function is fine, but we also want some sort of recovery guarantee that, there's a tree we want, and we want to make sure we're getting the right tree. So in particular, the sort of metrics that arise in the context of phylogenetics are ultrametrics. Those are the distance functions. And let's say your original similarity graph came from an ultrametric. So those similarity values are decreasing functions of the ultrametric distances, okay? Whatever the decreasing function is, okay? So a similarity graph has been generated as some decreasing function of ultrametric values. What can you say about the tree? And it turns out that the tree that minimizes this cost function is the generating tree for the ultrametric. Okay, so it's a recovery property, and that's a very nice recent result. Okay, so how does this thing work? Well, I tried it out on a very sort of a fun data set called animals with attributes, which is something like 75 animals, each of which has 75 features. And these features are things like furry, 4 legs, that kind of stuff. Okay, so the 75 animals, you have 75 attributes, so you can just run the algorithm on it very easily. And you get something, okay, a hierarchical clustering of the animals, and it looks great to me. Horse and deer and antelope, here a seal, killer whale, dolphin, looks great. So as far as I'm concerned, this is wonderful. But it turns out that, like, from the biologist's point of view, there are definitely some mistakes in here, okay? But it's very close, okay? And so we also tried average linkage, and that also did very well, very similar, okay? And so then the question is, what's the point then? It's like, okay, we put all this effort into finding a cost function. We tried to prove some stuff about it, and we have this algorithm now. And, it does kind of like what average linkage is doing. Was there any point to the whole exercise? And I think there was. And let me explain what it is. The first is that average linkage, although a wonderful algorithm, is quadratic. And that means that you simply cannot run it on very large data sets, 100,000 points, for instance. This, on the other hand, because it's top-down, you can look for quick and dirty ways of doing the sparsest cut in linear time, and so potentially get an algorithm that's only n log n. And so there are actually many ways in which one could try and do this, and this is something that we are investigating. The other thing, the other rationale for having the cost function is that you can then do constrained hierarchical clustering. And I'll just give you 2 examples of that, right? Why would you want to put constraints into hierarchical clustering? Well, here's an example. Suppose you wanted the clustering to be interpretable. Like you say, each split has to be on a single feature. That's easy if you have a cost function. You just say, instead of doing arbitrary splits, minimize the cost over splits of a certain type. And then you get an interpretable hierarchy. Okay, first check if the animal is quadrupedal and humped paws. I don't know what meat teeth means. But anyway, these are some of the features in this data set. Okay. The other sort of thing that, the other kind of constrained hierarchical clustering that I'm very interested in is the sort of interactive hierarchical clustering. And I'll just say a couple of words about that. You know, I really love unsupervised learning a lot, you know, but I do feel that, you know, when done right, it gives you something that's close to what you want, but it can never really give you exactly what you want, okay? Just, you know, even in the animal example, there are really a lot of ways to hierarchically cluster animals. You could be trying to get the Linnaean taxonomy, or some sort of geographic-based hierarchy, or just how cute they are. I mean, these are all legitimate, okay? And there is just no way that an unsupervised algorithm can figure out which of these you actually want, okay? So you can get close, but you're never actually going to get the one you want. And so for that, you do need some interaction, okay? And once you have a cost function, that's not so hard to do, okay? So what we did is we started with that tree, that animals with attributes tree that I showed you that looked pretty good to me, but, you know, has apparently got some mistakes. And then we started an interactive procedure. So what is the interaction? On each round, you randomly pick 10 animals, and then you show the hierarchy restricted to those 10 animals, okay? Because this is really too big to look at in one go. So you pick 10 animals at random, and then you show the hierarchy restricted to just those 10 animals, and then you ask the expert, which is not me, but you ask the expert, does this hierarchy look good? And for example, over here, although it seems fine, there are some problems, okay? And here is one. So it turns out that there should be a cluster that contains tiger and collie, but not gorilla. Okay? Maybe this makes sense to some of you. The tiger and collie should be together in some subtree that does not include gorilla. Okay? That's one of the things of the correct taxonomy. And so what happens is that the expert looks at this picture, looks at this random snapshot, and then fixes a little part of it, types in this constraint, and this then gets thrown into the, just gets thrown in as a constraint. And then you can say, minimize the same loss function subject to this constraint. And it turns out that algorithmically, that is quite easy to do using some tricks that people in phylogenetics have developed, because you know, they have actually also been interested in dealing with constraints of this kind. And so you throw in the constraint, and then you get a modified tree that satisfies that constraint. Okay, so now tiger and collie are together over here, and gorillas apart from them. And in this case, you do this a few times, and you get the right tree. Okay. So I think this is a very this is a very useful way of improving hierarchical clustering. Okay. Yeah.
Are you modifying the original tree, or are you modifying the weights that then get put into the hierarchical clustering algorithm again?
Right. So what happens? Right. So what happens is the cost function remains the same, but now there are these additional hard constraints. So it says, okay, the tree has to have some subtree that has these two, but not this.
So wouldn't that, in some sense, conflate where the problem might come from? So it might either be that the original cost function is problematic because the weights are not right, or the algorithm's approximation guarantee is such that it's not good enough to give you the right clustering for the given set of weights.
I mean, you can think of that original cost function as essentially some kind of regularizer. Okay, it's, you know, a reasonable cost function on trees. You know, it's certainly not going to give you the right tree, you know, right off the bat. it has no idea exactly what it is that you want. But then if you throw in a few constraints, it's like a regularizer. It does something reasonable subject to those constraints. Yeah.
But how do the constraints interact with the recursive calls of sparsest cut?
Right, so that's right. Okay, so that's the algorithmic issue of how we actually incorporate these constraints. And it seems a little bit tricky, but it turns out that these constraints like this are very hard to incorporate into a bottom-up scheme. But if you have a top-down algorithm, it's quite easy to incorporate these constraints. And this is just using there are some standard tricks that I use for this. Yeah.
So you could also plug in constraints that are classification-based constraints. Those are kind of a subset of these types of constraints anyway, right?
Yeah, I mean, this is actually just a toy example, but I think that, and this is a very specific form of interaction, I think ultimately what would be needed is just like a handful of different types of interaction, because sometimes it might be feature-based. Like you say, you really need to be looking at the quadrupedable thing or something like that, right? And so that would be a different type of interaction and a slightly different type of constraint, and it would be worth having a scheme for that. So, hopefully there'd be a handful of these different constraint types that would actually cover quite a few cases that arise in applications.
So why don't you put the constraints into you have some initial graph, right? But you could have weighted edges in the graph, right? And you could actually learn to predict what the weighted edges should be in the graph.
Right.
And then you could imagine you putting the constraints in as an example about what similarity and dissimilar should be. And then you could generalize from needing to specify a constraint for every violation of the initial cost function to only needing to specify a few so that you can kind of adjust a very large graph in a relatively small amount of time.
Right. So the question there is about here's another way to use the constraints, which is to actually learn the similarity function, right? And that's another thing that that's another thing that could be done. So one point worth mentioning is that you don't actually end up correcting every flaw in the initial tree just because there's this kind of there's a domino effect.
I guess that was similar to the question I was asking before, because the algorithm that's used to produce the tree is itself an approximation algorithm. And
Right.
if you have the perfect weights, you still might not get the perfect tree with respect to that weights because that's only an approximation algorithm. So the question really becomes, from an interactive learning perspective, what's the most efficient way to get to the final right tree? Is it to use these queries and these constraints to go back and correct the original similarity matrix, which might then give you a distorted view through the approximation algorithm? Or is it better to take the final result and then correct that final result via the interactive query?
Yeah, I'm not sure actually. Both these things, similarity matrices and hierarchical clusterings, these are the sort of the bit length for hierarchical clustering is something like n log n. And for a similarity matrix, it's something like n squared. These are both fairly complicated objects, and we can regularize heavily. But in both cases, you would need quite a few examples if that's all you were using. So that's something that really does come up a lot in interaction. Like there are certain types of interaction that have small local effects. There are types of interactions that have more trickled-out effects, and then there are types that are these sort of big sledgehammers that make that cause a big global change. And it's kind of it would be interesting to sort of quantify these things. And yeah, absolutely. So in terms of open problems, there are lots of them, but I'll just say one very quickly, which is, this was a case where there really was a lack of cost functions, and so, it made sense to introduce one. But I also think there are many cases in which we already have cost functions in which it makes sense to look for other ones, okay? So in a lot of unsupervised learning, the way we actually come up with a cost function is we posit a probabilistic model, mixture of Gaussians, LDA, and so on. And then the cost function is simply the log likelihood. It's sort of given to us automatically. But this can be unsatisfactory in some ways. Some of those assumptions we have to build into that probabilistic model are a little bit hard to swallow and perhaps unnecessary. And very often that log likelihood cost function that we end up with is just a huge mess. And we just, algorithmically, it's not something we want to deal with. We look at it, it looks horrible. And so we just say, well, we're just going to use local search or, EM. I don't want to have to, try and deal directly with this. So I think that there really is, that there's possibly something to be gained by actually looking at cases where we ostensibly already have these cost functions, like these log likelihoods of various types of models, and just go in and say, is there something similar that seems to be capturing some of the same thing that we could actually algorithmically deal with, and not just pass off to EM. Okay, thank you very much.
You must have thought about that. If you have statistical data, right, suppose you have some density function, then this kind of, you could have a clustering of the density function, right? And does this cost make sense in this kind of continuous case, or what would it be?
So are you talking about the setting where the data you get is generated from some distribution?
Let's say you have,
right. Right. So if you get data generated from some distribution, I think a lot depends on how you construct that graph. And so I think a very interesting question would be: suppose the data points are generated IID from some density, how would you construct the graph so that so this loss function would actually converge ultimately to something meaningful?
Or is there some sort of optimal for both?
I don't know. No idea. Yeah.
So how do you actually generate the similarities from the data and the experiments? So you need a graph that actually has similarities in it, right?
Yeah. So this so in those particular experiments, these animal experiments, this is a very simple data set. It's like whatever 80 animals and 80 attributes, and these are all binary attributes. It's a walk on two legs or not walk on two legs. So we just did dot products. I mean, the idea was not to try and get great performance on it or anything. It's just to quickly, it's like just basically as a quick sanity check. Yeah.
So have you used its cost function to compare different hierarchical clustering algorithms?
Oh, you mean to compare different hierarchies on the basis of this cost? I would, I wouldn't. This cost function is just something I cooked up last year. I mean, I wouldn't. I don't see it as as a rigorous basis for comparing different hierarchical clustering algorithms. Something that would be a lot more compelling to me is, if we actually had a nice test bed of hierarchical clustering data sets, and then we could compare against a gold standard or something like that. So that would be nice. Unfortunately, I don't think we have a test bed of that kind. There are a few data sets where there is this natural hierarchical structure, like this animals data, but it would be nice if there were more. Yeah.
Can you say something about the inverse problem? Like you have a tree, what are the ultrametrics that actually will pack this tree as optimal? Or what are other classes of similarities that are not ultrametric that will optimize to that? I realize it's a hard problem, but can one hope to say anything?
Right. So what happens? Right. So relating back to ultrametrics over there, the starting point, in these phylogenetic trees, the way in which it differs from hierarchical clustering is that you don't just have a tree, but you also have lengths on the edges, and so that, so I guess one could talk about as assuming those lengths are strictly greater than 0. What is the range of similarities that you would get from that? Yeah, and then this is something that was actually touched upon quite a bit in Varun Kanade's work. Yeah.
So what can you say about the stability about this cost function. Say your graph undergoes some random perturbation, you have some perturbation, let's say.
Yeah, so I mean, currently, right, okay, so about the stability of the loss function, right, as opposed to the specific algorithm. So the various greedy heuristics you could use to find the cut have very different stability properties. For example, the spectral ones can be wildly unstable, whereas some of the semi-definite based ones are probably a lot more stable. That would be something that would be really interesting to figure out. You know, both the stability of the loss function itself inherently and of the specific splitting methods. Okay.